Lie theory, named after the Norwegian mathematician Sophus Lie, serves as the foundation for understanding continuous symmetries in mathematics and physics. At its core, Lie theory examines the structure and representation of mathematical objects known as Lie groups and Lie algebras. Among the most influential concepts in this field are the Cartan Subalgebra and the Weyl group, both of which play critical roles in uncovering the symmetry and internal structure of complex algebraic systems. The Cartan Subalgebra offers a simplified yet highly informative perspective on Lie algebras by focusing on the most manageable and symmetric subset of their elements. This subalgebra allows for an efficient decomposition of the algebra into simpler parts, making it easier to analyze and classify Lie algebras. Meanwhile, the Weyl group captures the inherent symmetries of the Lie algebra's structure by reflecting transformations that preserve the algebra's essential properties. Together, these two concepts form the backbone of many classification results and representation theories in Lie theory. This exploration presents a comprehensive theoretical analysis of Cartan subalgebras and Weyl groups. It delves into their foundational principles, their significance in the broader framework of Lie algebras, and their profound implications in fields like geometry, representation theory, and theoretical physics. Before examining the specifics of Cartan subalgebras and Weyl groups, it is essential to understand the foundational concept of a Lie algebra. A Lie algebra is an algebraic structure designed to study continuous transformations and symmetries. It can be thought of as the infinitesimal counterpart of a Lie group, focusing on the local linear approximations of group operations near the identity element. Lie algebras are built on the principle of combining algebraic elements using a binary operation known as the Lie bracket. This operation captures the essence of the underlying symmetries and structures found in continuous groups. The key property of this bracket operation is its antisymmetry, meaning the order of operations matters in a precise, structured way, which mirrors the non-commutative nature of transformations in physical systems and mathematical symmetries. These algebras appear naturally in many mathematical contexts, especially in the study of symmetries of geometric objects in physical systems. Semi-simple Lie algebras, a particularly important class, possess no non-trivial ideals, meaning they cannot be broken down into smaller, simpler algebras. Understanding the structure and classification of these semi-simple Lie algebras forms the backbone of much of modern Lie theory. The Cartan subalgebra serves as a critical tool in simplifying the otherwise complex structure of Lie algebras. It can be described as a maximally abelian or commutative subalgebra, meaning that all elements within it commute with each other. This property allows the Cartan subalgebra to play a central role in analyzing the symmetries of the entire Lie algebra. One of the most important characteristics of a Cartan subalgebra is that it is self-normalizing. This means that if an element from the larger Lie algebra commutes with all elements of the Cartan subalgebra, then it must already belong to the subalgebra itself. This self-contained nature makes the Cartan subalgebra an ideal structure for studying the overall behavior and properties of the full Lie algebra. The significance of the Cartan subalgebra lies in its ability to simplify complex algebraic relationships. By focusing on a Cartan subalgebra, mathematicians can decompose the larger algebra into simpler parts that are easier to analyze. This decomposition reveals the fundamental symmetries of the algebra and provides a clearer picture of its internal organization. In semi-simple Lie algebras, the Cartan subalgebra is particularly important because it provides a natural way to classify the algebra's elements according to their interactions with the subalgebra. This classification leads to the development of root systems, which represent the fundamental building blocks of the algebra's structure. Each element of the Lie algebra can be categorized based on how it transforms under the action of the Cartan subalgebra, offering deep insights into the algebra's symmetry properties. The concept of a root system emerges naturally when studying how the elements of a Lie algebra interact with its Cartan subalgebra. A root system is a collection of elements called roots that encapsulate the essential symmetries of the algebra. Each root corresponds to a specific transformation property of the algebra's elements with respect to the Cartan subalgebra. These root systems exhibit remarkable symmetry properties. They can be visualized geometrically as collections of vectors in a Euclidean space, with each vector corresponding to a different root. The arrangement of these vectors is highly structured and reflects the underlying symmetries of the Lie algebra. A root system divides the Euclidean space into distinct regions, each corresponding to a different symmetry transformation of the algebra. These symmetries form the basis for understanding the action of the Weyl group, which is generated by reflections across hyperplanes perpendicular to the roots. The classification of these root systems is central to the broader classification of semi-simple Lie algebras. The structure of root systems is closely linked to the concept of simple roots, which are a minimal set of roots that can be combined to generate all other roots in the system. The relationships between simple roots are encoded in diagrams known as Dynkin diagrams, which provide a visual representation of the algebra's fundamental symmetries and structural relationships. The Weyl group captures the full symmetry of the root system and, by extension, the underlying Lie algebra. It is a finite group generated by reflections that preserve the structure of the root system. Each reflection corresponds to a transformation that leaves the overall structure of the algebra unchanged, even though it may rearrange its components. The action of the Weyl group can be visualized geometrically as a set of reflections across hyperplanes in the Euclidean space of the root system. These reflections generate symmetries that reveal the internal consistency and regularity of the Lie algebra's structure. The Weyl group plays a central role in many aspects of Lie theory. It governs the relationships between different elements of the Lie algebra, particularly in the context of classification and representation theory. The symmetry properties encoded in the Weyl group allow mathematicians to identify equivalent representations of the algebra and understand how different elements relate to each other. In certain cases, the Weyl group corresponds to familiar symmetry groups from other areas of mathematics. For example, in the case of the special linear algebra, the Weyl group is equivalent to the symmetric group, which describes all possible permutations of a finite set of elements. This connection highlights the deep and often surprising relationships between Lie theory and other branches of mathematics. One of the most powerful applications of Cartan subalgebras and Weyl groups lies in the field of representation theory, which studies how abstract algebraic structures can be realized as concrete linear transformations. Representation theory provides a bridge between abstract algebraic concepts and more tangible mathematical objects, such as matrices and vector spaces. In the context of Lie algebras, representation theory focuses on understanding how the elements of a Lie algebra can be represented as matrices acting on finite-dimensional vector spaces. The Cartan subalgebra plays a crucial role in this process by providing a framework for decomposing the representation space into simpler components called weight spaces. Each weight space corresponds to a particular eigenvalue of the action of the Cartan subalgebra, and the collection of these weight spaces forms the basis for analyzing the entire representation. The Weyl group acts on these weights, generating symmetries that reveal the underlying structure of the representation. A key concept in this context is the notion of the highest weight, which characterizes the most dominant symmetry in a given representation. Every finite-dimensional irreducible representation of a semi-simple Lie algebra can be uniquely determined by its highest weight, providing a systematic way to classify and study representations. The action of the Weyl group ensures that weights related by symmetry transformations are treated equivalently, simplifying the analysis of complex representations. This symmetry also leads to elegant mathematical results, such as the Weyl character formula, which provides a systematic way to compute the character of a representation based on its highest weight and the symmetries of the Weyl group. The theoretical significance of Cartan subalgebras and Weyl groups extends far beyond pure mathematics, influencing fields as diverse as geometry and theoretical physics. In geometry, Lie groups and their corresponding Lie algebras model the symmetries of smooth manifolds, providing a framework for understanding continuous transformations and the geometry of curved spaces. The Weyl group plays a particularly important role in the study of symmetric spaces and flag varieties, which are geometric objects characterized by their high degree of symmetry. These spaces often serve as the setting for problems in representation theory, algebraic geometry, and differential geometry. In theoretical physics, the influence of Lie theory is even more pronounced. The classification of fundamental particles in the Standard Model of Particle Physics relies heavily on the representation theory of Lie groups and Lie algebras. The symmetries described by Cartan Subalgebras and Weyl groups correspond to fundamental conservation laws and invariances in physical systems. Gauge theories, which form the foundation of modern quantum field theory, are deeply connected to the structure of Lie groups and Lie algebras. The internal symmetries of these theories are described by the algebraic structures studied in Lie theory, with the Weyl group capturing essential aspects of the gauge symmetry. Additionally, in string theory and conformal field theory, the symmetries encoded by Lie algebras and their corresponding Weyl groups play a central role in understanding the behavior of physical systems at the most fundamental level. The geometric interpretation of these symmetries offers profound insights into the structure of space-time and the fundamental forces of nature. The theoretical framework provided by Cartan Subalgebras and Weyl groups represents one of the most profound achievements in modern mathematics. These concepts offer a deep understanding of the symmetry and internal structure of Lie algebras, enabling the classification and analysis of these complex algebraic systems. The insights gained from studying Cartan Subalgebras and Weyl groups have far-reaching implications, extending to geometry, representation theory, and theoretical physics. The unifying power of symmetry, as captured by these structures, continues to inspire new discoveries and deepen our understanding of the mathematical foundations of the physical world. Élie Cartan's pioneering contributions to the classification of Lie algebras and Hermann Weyl's groundbreaking work on symmetry and representation theory have left an indelible mark on the mathematical landscape. Their ideas continue to shape modern research and influence diverse fields, from quantum mechanics to algebraic geometry. As Lie theory evolves, the concepts of Cartan Subalgebras and Weyl groups remain central to new developments, providing a rich framework for exploring the deep connections between algebra, geometry, and physics. These theoretical constructs not only illuminate the structure of mathematical symmetries, but also reveal the underlying harmony that governs the universe's most fundamental laws.